Hello guys, in this video we are going to discuss about the principal component analysis. So we have started with the non-parametric techniques and we had seen the Parsons windows technique and we had also seen the k nearest neighbor technique. So you see that we are always storing this training data for these classification techniques. So here the data is to be stored. Also in k nearest neighbors, the data is to be stored. Now when the data has a lot of dimensions, say this is 2 dimensions, so it is okay. But then if it is in 100 dimension, 200 dimension data, where you have 100 features for a particular image or anything, you have 100 features in your data. So at that time storing this data also becomes difficult because it will require a lot of memory to store so much of data. So then one will want to compress this data, and this technique can be done using the principal component analysis. So principal component analysis is one way by which you can compress your data. So let us first visualize what the principal component analysis is doing, and then we'll go with the mathematical proofs. So consider that suppose in 2 dimensions, so for representation purpose I'm using 2 dimension, but this can be extended to 100 dimensions, 200 dimensions, etc. So suppose I have a 2 dimension data which is somewhat like this. So here you can see that the variance in this direction is very less. So this particular thing can actually be approximated as just this much. So even if suppose this data is just this much, it is okay. Means it is, we are losing data, no doubt we are actually losing this much of data, but then the essence of the data is still intact. So if you consider this particular data, you can see, say, the variance in this dimension, x1 dimension, is this much. So in x1 dimension the data varies from this point to this point. Say I have a point over here also. And for this x2 direction the data is varying from here to here. So you can see that essence is still maintained over here. This variance and this variance are still maintained. So here you are losing data, no doubt I'm going to lose some data, but then it is a very effective loss of data, so that is not hindering a lot of things. So let us see how can we achieve this. We want to go from here, we have this data, and we just want to, what we say, remove sort of this dimension data, this dimension. So for that, first we will need a transformation such that my new transformation has axis like this. So this was my original data that I had. Now I will do some transformation that we will see in the mathematical proof. So with that transformation, the data which was like this will now become like this. So you can see here the axes have changed. So initially the axes were my features x1 and x2. Now I'm going into some different space where my axis is e1 and e2, which is inclined like this. So it can be seen as a shift of axis or something like that. You're just shifting and rotating the axis. So this is very nicely possible by our linear algebra matrix method, and this is what we are going to see. That is the whole crux of principal component analysis. So you can see in this E1 E2 space the data will look somewhat like this. Now next what I am going to do is I am going to basically project all of these data on this axis. So it is like I am projecting all of this data on this axis. So it is not that I am just removing the data, I am projecting the data on this axis. So further I can have the reconstruction possible. So now all this data I am projecting over here. So it is like if there is a line like this, a slant line, so I can project the slant line like this. So this is what we have done in vectors, the projection of a line on this. Similarly, I am projecting all these points on the even axis, and then I am just going to remove the E2 axis. So what we are left is only with this middle axis data, which is over here. So now I just completely removed this E2, because you can see that it does not really matter. This variance is so small that even if I remove, I have the crux of the data. So I've just removed this E2 and I've got this. Now we were in this space. So now from here even we are going back to the x1 space. So when we reconstruct, we will get something like this. So since I removed the E2, so actually there was this E2 over here, which you can see over here, but since I removed this is what is my compression. So I am just removing this E2. So there is some loss of data, no doubt, but then it is an effective loss of data. So I am removing this E2, and this is what I am getting as my output. So that was the desired output that I needed. I just wanted to compress this with the line. So now you can see that even if I use this data or this data, it will not make that much of difference. It will make difference, but we'll see how much error or what sort of some things come into the picture. So this is the basic visualization of principal component analysis. We have our data, we are just transforming into a vector space where the axes are inclined towards the maximum variance and the other variances and orthogonal to it. So these both are orthogonal, and then we effectively remove the direction where the variance is very less. So here you can see the variance is very less, so we are just removing this direction, and we are reconstructing, we are going back to our x1 x2 space, and we have this particular thing over here. Okay, so that was about the visualization. Now let us see the maths behind it. So the covariance matrix, that is Cx. So we talked about variance right over here. We saw the variance of x1, we saw the variance of x2, and we saw that it is not quite hindered over here. So hence we'll start with the covariance matrix. We'll see, say, x1 x2. So this is the covariance matrix of x. So here x is nothing but x1 comma x2. X is having features x1 and x2. So the covariance matrix can be given by sigma 11, which is basically the variance of x1. So this spread is nothing but sigma 11. This spread is nothing but sigma 22. So that is the variance of the second dimension feature. And sigma 12 and sigma 21 are nothing but the covariance, or we can say what is the relation, correlation basically. So what is the relation between x1 and x2? So you can see that as x1 is increasing, your x2 also tends to increase. So here, say this point, x1 is this much and x2 is this much. As you go on increasing x1, you get a point where the x2 is also increasing. So this can be termed as positive correlated. So when one feature is increasing, the other feature also tends to increase. So that these things are given by sigma 21 and sigma 12. So also please remember, sigma 12 will always be equal to sigma 21. So this is a property of the covariance matrix, that it is symmetric. So all these will be equal. So this I was just talking about two-dimensional space, but in actual reality you can work with any k dimensional space. So here I have here k is nothing but dimensions, so you can work with any k dimensional space, 100, 200, 300, any dimensional space you can work with. Okay, so that was about the covariance matrix. So what is our objective from here? First we want some axis or some transformation. So we want to transform this vector space into this vector space. And what is the condition that is needed? The condition is that over here you can see that there is some correlation. As x1 is increasing, y2 x2 is also increasing, sort of. This is positive correlation. So in the transformed space we want axis is such that there is zero correlation, there is no correlation. So here you can see even if E1 is increasing, the E2 is remaining constant. So if you take a point over here, this point, you can see that its E1 is this particular value, but for a point over here the E1 has increased, and since E1 has increased and still E2 is remaining the same. So this particular thing can be termed as uncorrelated. So this is the other major thing, that we need one vector space, or we need a transformation. So we have to transform this particular space to this space such that our data becomes uncorrelated. So that is what we have to do. So this is so first let us see some properties of the covariance matrix. So one of the properties is that it is symmetric. So the eigenvectors are orthogonal. So this is one of the very important properties of covariance matrix, that its eigenvectors are orthogonal. Its eigenvalues are real, positive semi-definiteness. So for any covariance matrix, so this can be a covariance matrix of any vector, any particular random vector, the covariance matrix will always be positive semi-definite, which means that this condition will be true. This also means that the eigenvalues will be positive and the determinant will be positive. So I will come back to this. Also I will, I guess, upload a video for more beauty of this positive semi-definiteness. So we'll see what this is in another video. That will be for an next video. That will be some other video, not in this course. So now our objective, the first objective over here is, I want to transform this data from this to this. So this is correlated data. I want to uncorrelate this. So I want to make data uncorrelated. That is my first objective. So let me consider that this space is the new y space. So y space has some E1 and E2. For now, just take these notations. You will understand slowly why I have chosen E1 and E2 for this this space. So here let this space be a y space with vectors E1 and E2. Okay, so what I want is, I want uncorrelated data. So the covariance matrix of y, the covariance matrix of this data, should just have some variance in E1 direction, some variance in E2 direction, and it should not have any, what we say, covariance. So when I write this term, so this should be actually lambda 1 1. So with this notation, so this is like lambda 1 1, this is lambda 2 2, and then you will get lambda 2 1 and lambda 1 2 and lambda 2 1. So this should be 0. That is what we mean by uncorrelated random vector. So this space, the data in this space is uncorrelated, so it should follow this particular thing, that its covariance matrix should be like this, of this sort. So it should be a diagonal matrix actually. So that is what we want. So this was for two-dimensional data. In general, it should be just a diagonal matrix with all zeros over here and all zeros over here. That is the actual task that we want. Okay. So in order to do that, in order to do this, we will have to diagonalize we have the covariance matrix of this. So we have Cx. From Cx we have to find out Cy. So we have Cx because we have the data. Now from Cx we'll find out Cy. So for that, what we'll do is we'll diagonalize the covariance matrix. So this is a very good term in linear algebra. So to diagonalize any matrix, what we do is we take its eigenvectors. So we have this eigenvector equation Cx. So the actual eigenvector equation is Ax is equal to lambda x. So similarly for the covariance matrix Cx, where Cx is given by this. So the Cx into some x dash, so this x dash is the eigenvector of Cx, is equal to lambda x dash. So it is equal to lambda times, so lambda is the eigenvalue into x dash. So now I am just substituting the values and let's see what happens. So sigma 1 1 sigma 1 2, so this is nothing but Cx, and I have one eigenvector, that is x1 dash x2 dash. This equals lambda x1 dash x2 dash. So this x1 dash x2 dash is nothing but the components of the eigenvector, and this particular equality holds because this is the eigenvector. Now if Cx is n cross n, okay, so let this be k cross k. Right, so I am having a k dimensional covariance matrix. So if Cx is k cross k, it will have k eigenvectors and k eigenvalues. So if it is k cross k, it will have k eigenvectors and k eigenvalues. So I can have a matrix over here such that here the first eigenvector, so this will have two eigenvectors, say x dash 1 and x dash 2. So these are two eigenvectors of this particular thing, and these will have lambda 1 and lambda 2 as eigenvalues. So what I am doing is I am putting x1 as a column over here and x2 as a column over here. So this is what I am doing. So by this what we can do is we can write it like this. So this is the same x1 dash and this is the same x2 dash, the two eigenvectors, and this can be multiplied with a diagonal matrix which is nothing but lambda 1 lambda 2. So to visualize this, it is like when you are multiplying this into this plus this into this, you are getting lambda times x1 plus lambda times x2. The same thing, say this is some x1 dash, so this will be lambda 1. So here you can see that this is this plus this plus this, and this plus this will give you this and 0 and this and 0. So you can see the second term is becoming 0, so you get essentially this into lambda 1, which is what we have got over here. So this is the important thing that we are focusing on, because we have to make a diagonal matrix. We want our Cy to be diagonal. So this is that we want over here. So in general, so this was just for 2 cross 2, so I just wanted to show you the visualization. So in general it will be Cx into some u, so this I can term as a u vector, where u is a matrix with its columns. So its columns are the eigenvectors. So this is the first eigenvector, this is the second eigenvector. So I can write u1 as x1 dash x2 dash, where x1 dash and x2 dash are eigenvectors. So I can write like this. So this is again u, and this is, so this I am terming as capital lambda, where capital lambda is nothing but a diagonal matrix containing all the eigenvalues. So these lambda 1 and lambda 2 are nothing but the eigenvalues. So I can write this. Next, I can pre-multiply by U transpose on both the sides. I am pre-multiplying by U transpose on both the sides. Here you can see that this particular thing will become I. The reason for this is that eigenvectors are orthogonal. So eigenvectors are orthogonal says that all u's are eigenvectors. So this is the first eigenvector, the second eigenvector. When I am multiplying it with U transpose, the first eigenvector is getting multiplied with the first, the second, the third, like this, all eigenvectors, and only for the first it will give 1 and for others it will give 0. So this particular thing holds because U is orthogonal, because all the vectors inside them are orthogonal. So this becomes nothing but I, the identity matrix, into the capital lambda, and the capital lambda is nothing but this thing. Now I'm just exchange these terms, and you can see that this is our required covariance. We wanted a covariance like this, where these are just diagonal values. We saw that we wanted Cy such that it has all diagonal values. This was our objective, right? We wanted uncorrelatedness, which means this. So I want my Cy to be this. So now I've got my Cy, so I can just replace this by Cy. So I'm just changing the notation because now I know that this is Cy, this is what I want. So I'm making this as Cy. And how can I get Cy? I have to multiply Cx, which I have. This is known to me because I know the data, so I know the Cx. This will be multiplied to U transpose and U, so pre-multiplied by U transpose, post multiplied by U, where U is nothing but a column. It is a matrix with columns having eigenvectors. So I am just doing a little math. So now this is the covariance matrix. So I found out that what will be the covariance matrix of this particular vector space, but now I want to transform it. So I need a transformation such that every x over here gets its mapping somewhere over here. So a x over here, so a point over here should get some point over here or something. So I need this mapping. A point over here will be which point in this space. This mapping is important. So that is objective now, is to find y from x. We have this x, we have our data. From this data we have to go to the y space. So I know if suppose this is the point, I should know this point corresponds to which point in this space. So that is what I have to do. So this is what I have got from the previous equations. Now it is just simple. I am just expanding Cx. So Cx is defined by expectation of x minus x bar transpose. So this x bar is nothing but the mean vector x. So x bar in this representation will be this. This is the mean of this data, right? So this is the definition of covariance. Next, I am just replacing x minus x bar as z because that is convenience. It is easy to write like this, nothing else. So this is the next thing. Now, since u is not dependent on e, because this data, this expectation of this data, so u are just eigenvectors which is not dependent on this data. So I can put u inside the expectation. So I've just put u inside the expectation. Now what I can do is I can write this like this. So we know that AB the whole transpose is B transpose into A transpose. So I have just taken the whole transpose, and this thing will not get transposed, this will get transposed and it will get flipped. So this is what I have done. So this thing I can write it as some y. So it is like covariance of y will be some E of y transpose. So this is because here the mean is 0. So I am transferring in such a space where the y bar is nothing but a zero vector. So here I had some x bar which was this mean, but here the y bar is 0, so I can write it just as y transpose. This is equal to this thing. So by comparing, so you can compare that this is y into y transpose, this is expectation of u transpose z, u transpose z transpose. So this thing can be considered as y. So there is this, so this is y transpose, this is y. So by this I get y is equal to u transpose z. Just plugging in the values of z, so you will get your required transformation. So when you just take the data, so you have any point, say I have this point, you just minus this point from x. So when you minus this point from x, so basically what will happen is the data will shift over here when you minus this, so this will come over here somewhere. And next you have to multiply this particular thing, so you have to multiply this x with the eigenvector. So you will have to multiply this with u transpose, which is nothing but the eigenvectors of this particular thing, a covariance matrix. And when you do that, you will get this transformed over here. Similarly, when you take suppose this point, you will first minus it with the mean, so it will come somewhere over here, and then when you multiply it with u, you will get this point. Then you take say this point, that will come somewhere over here, and this will come over here. So actually it is, when you minus it by the mean, you will get something like this. So when I'm minusing this whole data with the mean, so this is nothing but x minus x bar that I've plotted over here. And then when I multiply this with the u transpose, it is going to give me this, because it should be uncorrelated. So that is what condition we have find out. So by this transformation, our data is uncorrelated, or this transformation decorrelates the data. So I guess this is enough for this particular video. In the next video we will see what is the direction of E1 and E2, and we will see how can we remove this E2, that is the minimum direction, and get this. So that's for the next video. Thank you so much for watching. Thank you.